Right. So as I said earlier on, we are swapping the section instead of exploratory data analysis. We are leaving that one for now, but we are diving into supervised uh, machine learning and an overview of decision trees and random forests. Because I can't find the material for the exploratory data analysis in the tree folder, so we will sort that one out later on. So two flavors of machine learning is first, find the structure in the data, which we normally refer to it as unsupervised. So you will be given some input data without any output. So like x1, x2, x3 to xn, and then you might want to find some pattern or anything. So in this case, we take advantage of unsupervised machine learning to explore the data. And then you can see from here, this is divided into two clusters or two classes. Function mapping from data features to classes, that is supervised machine learning. So that is where the name comes. So supervised is, in the case of supervised machine learning, you are dealing with input and output. So it depends on the number of variables or input variables. But most of the time, we will come to look at some, uh, even under supervised machine learning, there are what we call regression or classification. So if it is a regression, you will map the input to a particular output. But in terms of unsupervised machine learning, you don't need to map the input to a particular output. You're only dealing with the input variables. So this is the major difference between supervised and unsupervised machine learning. And for instance, here for the supervised machine learning, we have inputs, let's say x1 to xn, and then we have the the output, which we normally refer to them as labels. So y1, y2, y3. So uh, we have first input variables goes to the first output variable. Second row or second sample goes to the second output variable, and so on and so forth. So the number must be equal. Number of samples or rows must be equal to the number of what output that we have. So this is just a diagram that represents or describes the supervised machine learning, which deals with inputs and then output variables. So a workflow for machine learning. So we normally, if you just have your data, even if the data is labeled, that is, it has set of inputs associated or mapped to a particular output, it's good to start with unsupervised. Then you go for supervised learning. So often start with unsupervised learning to identify useful features or to extract, then run supervised learning method. Sometimes, if we have many inputs, we want to just go for the most important one. So we can do that by utilizing unsupervised machine learning algorithms. And then when we extracted the important features that we have, we can now feed them into supervised machine learning and then see how it works. So supervised learning start with feature extractions. I'm not sure if you covered this yesterday in the course of yesterday's presentations, but looking at it, what do we mean by feature, and also what do we mean by feature extraction? So you start with a matrix X of extracted features. So let's say these are some inputs. We have the first one, the second, and the third, different type of inputs, and we want to extract some features from them. So for instance, for the first data, we have some X features. For instance, big, webbed feet, quarks. So this might be some features that are that are used to describe this particular data. And this is also another data. These are the features. So it also has a feature called big and then webbed feet and then quarks. And another one. What about this one? So for this start data, raw data, if we say we're going to use features like big, web feet and quirks to describe this, we are doing the wrong thing. That is why we have wrong XX here. So this is wrong features for describing this data, but these are correct features that we can use to describe this data. For the first one, there's a question mark on the second feature, which is web feet, because we cannot see it here. So make sure at any time you use the appropriate and suitable features that describes the type of data you are working with. So these are the features that we can use to what? To predict this particular entity or component. So going forward, these are the features which are the input variables, and then these are the what output variable, which is y, that is the class. So we want to classify this. Let's say we want to carry out a classification task and to classify this type of what component of or entity. So if we train a machine learning model with these features and then we associate this feature to a output or a class called is a duck, right? We're doing the right thing. The same thing, we can attribute these features to a class that is what referred to as, this is also a duck. These are features that classify a duck. But if we use these features, X is not a duck. Why? Because this particular component is not a duck, and then the features that we use to describe it are wrong features. So make sure that you use the right feature. Excuse me. Use the right features for any entity or component that you want to classify, predict, or any tags on it. So under the covers, we say supervised learning finds a function to map from values of X to values of Y. So that's what we do. So for this, for instance, what we have just saw, these three features describe a what? A duck. So we have three features now: big, web, feet, and then quirks. And then this goes into the machine learning model. And then the machine learning model asks a question, or we are asking the machine learning model a question to tell us, if we have these features, what is the component or what is the entity that is likely have this attribute? And then the machine learning model, after being trained well, it will tell us that given these features, I think, or I believe that the component or the entity is a duck. That is the output now. Okay, so you impute the features into the model, and then the model output what? The entity or the component that has these features as its attributes. So won't always be perfect. Machine learning models are not always 100% perfect. So the goal of machine learning model developers is to what? Is to minimize the error, or what we call the loss function, right? So when we start, when you start your program properly, this is what you will be doing. If you have a model, machine learning model, you train it, you measure, you use some metrics, performance metrics, to measure the performance of the model. Let's say if you're using accuracy, you train the model and then you find out that the accuracy is, let's say, 50 or 60. That is not it's not good enough to conclude that this machine learning model will work perfectly. So you need to find a model that has an accuracy of 90 and above, or 80 and above. So all that you are trying to do is to minimize the error, the prediction error, or to increase the prediction accuracy. In other words, we are trying to minimize the loss. Then prediction, right? So we have this class, or we have outputs, and Y predicted class is a duck. So how well the classifier does on its training data may be different from how it does on completely new data. So these are the features. If we use these features for the first one, and then the model predicted this as a duck, fine. And then so what are the types of supervised learning that we have? Classification is one of the tasks that you will be coming across when you start your program properly. And some of you that have prior knowledge or experience in supervised machine learning, you must have carried out some classification tasks using certain machine learning algorithms or models. So in classification, we say Y is categorical. That is, each value is from a finite set. An example, let's say nationality. You want to classify people based on their nationality, or page will be clicked on. You want to know, let's say a binary classification, 0 and 1. 1 is when page is clicked on, and then 0 is when page is not clicked on. And then let's say you want to classify item, either this item is a dark or it's not a dark. All right. So we deal with categorical uh, uh, data here. And then when we come to regressions, the output, which is Y, is continuous. That is the data type now, is continuous. And in this case, we mean each value is numeric within a continuous range. An example is, let's say, age. Remember? So you want to predict the age of people. You are predicting a numeric value. You want to predict dollars some people spend based on their, sorry, let me plug this system on charging before it goes up. So you want to predict what individuals spend. So it might be in the form of what? In the form of numeric value. So this is what we refer to them as continuous. Okay. Right. So this has to do with the output variables, either categorical or continuous. And then so classification, let's look at what classification is. The process of building and evaluating a classifier. That is what we classification in machine learning. And look at these block diagrams or workflow. You start by training the model. Here we assume that you've got your data sets. Then maybe you have carried out the pre-processing activity on the data set, and then the data set is ready to be fed or to be used by the machine learning classifier. So the first thing to do is to train the classifier. And what do we normally do when we train a classifier or we train a machine learning model for classification? We are trying to find the function from X to Y, and then the fit parameters. So you are trying to find parameters. There is machine learning parameters, what we call machine learning parameters. What are the best or optimal parameters that now map the input variables to the output variables well, or the best fitting parameters? So we are trying to minimize a function when we train it, and that is what we call our loss function. So whenever we minimize the loss functions, we are trying to minimize the errors between the values that the machine learning predicted from the real values that we have. Yeah, maybe some of these terms may sound technical, but with time, you will become familiar with this. And then validation, the next component is validate, which is optional, right? These are nowadays, sometimes we can skip validation, is optional. So validation is now you tune the parameters and then choose from multiple models. And then the final thing is then you test the trained model. Testing the training model means assessing the performance of the model. And let me say something here. If you want to carry out these three tasks in developing a machine learning model, then you need to split your data into training, validation, and testing sets. But if you don't want to do validation, then you need to split your data into two, that is training and test. All right, so we can see this maybe in subsequent slides. Let's move forward. So why the three stages? Why the three stages? That is the stage of training, validation, and then testing. So challenges faced in building a classifier. First, the goal is to learn from training data, not only learning, but to generalize well. We want a machine learning model that will generalize well. What do we mean by generalizing well is a machine learning model that will do well on the training data and also do well on the testing data. But if the machine learning model performed well on the training data and then poorly on the testing data, it means that the model is not generalizing well on the data set. So we are trying to avoid the risk of overfitting on the training data. All right. So this term overfitting, you must have heard it before. As I said earlier on, overfitting is a process where the machine learning give a very good accuracy on the training data, let's say 98% accuracy, but when you supply or you provided the testing data, the accuracy drops drastically. Let's say in a process where the difference between the accuracy the accuracy difference between the training and then the testing is huge, then we can say that this model is overfitting and it might not be a good model. It might just be deceiving people, right? So validation data help us to compare different classifier settings, that is each trains on the training data to see which is better. So to avoid overfitting, normally we try to validate the model first before testing it. That's what validation does. So after validation, then test data. So test data help us to evaluate the final classifier by comparing its predictions against the gold standard. So we use the testing data to compare what the machine learning predicted against the gold standard. Gold standard here means the real values. See whether there is a huge difference or the difference is insignificant. So training may be computationally costly, especially neural networks. If you have sophisticated neural networks, the training may require more computational resources. That's why sometimes we go for HPC facilities. That is, what do we mean by H? Uh, high computational performance facilities. And sometimes you are using Google Colab. I think you must have started using it yesterday. But even the free version of Google Colab sometimes you may run into trouble because of the computational resources of some machine learning model. But in solving some simple problem like regression problems, you might not have problem. But when you start dealing with image classifiers, which deals with a huge data set and very complex big data set, you may need high computational performance resources. So Python provides a standard interface to many classifiers. That is a package that we call scikit-learn in Python. If you use this package, it has a lot of classifiers, a lot of regressors that you don't need to write the, their codes from scratch. What you need to do is just to what? To call them and then utilize them. All right, there's a question here. Say, is this why Google was labeling people as gorillas alone? Yeah, it might be the reason, Craig, because if you develop the machine learning using wrong features, it might end up misleading, mislabeling, misclassifying. All right, it's one of the reasons. Yeah. So let's move forward. We can address some of these questions maybe towards the end of the presentation. So scikit-learn provides a standard interface that looks like this. If you look at this code, so create a classifier. So CLF is just a variable that we use to assign this classifier to it. So classifier, and then you put the parameters, my parameters. So you need to parameters is what you will be working with. Maybe during your hackathon, you may be given some sample code, and then the sample code, you run it, it will give you the result, but you will find out that the accuracy is not what you want. So your task is to find the suitable parameters for that model that will what? That will yield or will lead to a higher accuracy, and you need to be tweaking them and then playing around with different parameter combination in order to come up with the optimal one. There are some algorithms that you can use, and then they can help you to get the optimal parameters. But You need to do a little research on that. So here you say X and Y. So X is the training data futures, N rows by D dimensions. So depending on the number of futures that you are dealing with, rows stand for records. So if you have 100 records, they are represented by the rows, and then the D stand by represent the column. That is number of input variables that you are dealing with. The previous example that we see is just 3 futures. So in this case, D, it will just, D dimension is 3. All right. So we have only 3 futures, but number of rows determines the samples that you have, number of records that you have. And then Y, which is the output, is the actual class. That is the training data for each of the N rows. So once you just write this line of code, you are now calling this classifier from scikit-learn package, and then you are assigning it to a variable called CLF. So the next thing is to train the classifier, and then the trained classifier, one line of code suffices. It can do it. So CLF.fit. Fit is a function that is used to train the model or the classifier, and then you supply what? Parameters, argument into the function x, y. So you are mapping the input to the output. We remember we say x is for the input and then y for the output. And then next is evaluate over new tests. So predicted y test data, this is also a variable, equals to clf.predict. Remember the dot product, we normally use the dot to access anything. All right. So is it like a dot product? Some of you that are from mathematics, the dot product, you know, when you say y x dot so that you are now calling something using the dot. So we are calling this function predict using the dot, and then we are supplying some argument into this function, which is x test data. So already this assumes that we have already split our data into training and testing. So remember, for the fit, this is a line of code that performs the training, and then this is a line of code that performs the testing. So you are now supply x test data. It's assumed that you have already have your data set, and then the name of the file that contains the data set is x underscore test underscore data. So you are just calling this data set here using the name, and then everything will now, once you run this code, the machine learning will be tested, and then the next thing you just need to know, if you define some parameters, let's say accuracy or prediction error, then you will see some values that tells you how the machine learning or how the classifier performed. So explainable classifiers, or let's talk about decision trees now. Please see the companion notebook. I think you have access to all these folders, right? So if you have access to all these folders, you can run them at any time, and then you can see to yourself how these things work. So explainable classifiers, one of the explainable classifiers that we have is the decision trees. Let's look at an example here. So we have these cards. Let's say it's a class that we want to classify, but we need to know what features extracted that will best describe this card, so that we can use them to train a classifier that whenever certain features similar features are supplied, the classifier will be able to classify uh, something like this. So suppose we want to predict if someone is going to buy a pet Y, given 4 features in our input matrix X. Okay, so we have black, fury, small, active. So these are the features. All right. So we have number 1 feature is black, and then it has this value. Fury has this value, and then small has this value. Active has this value, and these are the outputs. So for the first sample, the output is 1, which means Binary classification, you have two output, either 1 or 0. If it is 1, the prediction is true. It's predicting the right thing. If it is 0, it's not predicting the right thing. Right? So for the first combination, the output is 1, which is right. For the second combination, the output is also 1. It's not well aligned. Sorry. This and then for this output, these are the outputs. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have 5 rows, that is 5 samples or 5 records in this data set, and also we have 5 outputs. But each row or each sample or each record has how many futures? Has 4 futures. 1, 2, 3, 4. So which single future best predicts this? So look at it here. The intuition here is determine how well each future predicts the output. So we have for the black, this is what we call true value and then false value. Some of you that might be familiar with what we call confusion matrix. Okay, a true and then false. So we have for the black future, we have 2 that are true and then 0 that is false. That is for the first ones, and then here also here for the true under the second row, we have 1 and then 2. So these are the futures, and then these are the outputs. This also look a bit abstract. So look at it here. We say this equals to Fury correct 3 times. It's correct for 3 times, and then black correct 4 times, and then for smalls, and then equals to small correct 3 times, and then for active, not active, correct 3 times. The most important thing is know the futures and then know the output. Okay, if you are doing binary classification, you want to classify something as either this thing is cat or not a cat, then you might have 2 outputs. The output should either be 0 or 1. 0 means it's a cat, and sorry, 1 means it's a cat, and then 0 means it's not a cat. And then you might want to know the futures that you want to use to predict, to carry out that prediction. An example, using black to predict. So using black to predict. So what do we have here? So black, fury, and then small. So if we are using black to predict, so if black is 1, then all these ones are 0, which means the output is 1. And then if black is 1, and even if others are 1, the most important thing is we want to just use, if we are using only 1 futures to predict, we must get this future with a value of 1. So if black is 1, the same thing, we have our y is 0. But look at this. In this case, if we are using black to predict these cards, then what do we have here? Black here is 0, 1, 1, 1, and then it gives the output here 1, and then 0, 1, 0, 0. This is 0. So this is more of what do we call it now? When you deal with zeros and ones, logic, right? I can't remember well, but logical operations that you are dealing with 0 and 1. There is a table that we call it. Some of you. So if the animal is not black, or if the animal is black, small. So a flowchart for making predictions. Is the future or is the animal black? First, you start with asking questions. So if you are from computer science, you know what flowchart is. So when you have this symbol, it's for asking question, and then the next thing is it true or false? So is the animal black? False. If it is say false, then you ask another question. Is the animal small? But let's click and see what is happening here. So is the animal black? You say no. That is false. So it's not true. And then another question, is the animal small? This one goes to false. If it is false, you activate this one. If it is true, you go to this direction. So flowcharts always give us direction of how the final decision is being taken. So building a decision tree in scikit-learn, decision tree is more like flowchart. You take a decision, keep on splitting it. A decision tree, as the name implies, is a tree. From the tree, you go to branches. From branches, you go to the leaves, and so on and so forth. So you have what we call nodes and branches and then leaves. So you call using the scikit-learn, you call this is the name of the classifier that you shall be calling. So CLF equals to tree.decision tree classifier. This is inbuilt in Python, so you don't need to write code for it. And then criteria, what criterion I'm using is entropy. Later on, we'll see what criteria is. We will not be using entropy. Nowadays, decision tree use what is called Gini index. You use the criteria of Gini index to arrive at the final destination or final prediction. And then here is just training the model using the fit function. So CLF dot, you call the fit function and then you supply the input and the output. And then tree.plot underscore tree. This one is just plotting the tree now. You want to plot the tree to see what is going on. So CLF.fit XY. So at the right hand side, you see, is what we started looking at. Black less than equals to 0.1. So the model make use of these values to go from one step to another. And then this is the value for the entropy. That is how this entropy is being calculated. It's a mathematical function. So at this stage, the value for the entropy, that is, let's say at the first decision, the value of the entropy is 0.97. And then how many samples? We have 5 samples. That is 5 records. And then value equals to 2 and 3. This is an array. So from here, it now got splitted into 2. And then give you the value for the small, and then for the entropy, and so on and so forth, until the final decision is taken. So the summary here is decision trees. The basics of decision trees, we say a decision tree is a simple flowchart for deciding on whether an item belongs to a class or not. Yeah, decision tree is just understand it from the point of flowchart. You ask this question, if this condition is fulfilled, what next? Is this a black animal? Yes. Is this? Yes. Is this? Yes. If all the conditions are fulfilled, then finally, this is a cat. But if the conditions are not fulfilled, it will, at the end of the day, it will tell you this is not a cat. So this is how a decision tree performs operation and then to decide or to classify things, whether it's a cat or it's not a cat. All right. So by asking so many questions, and then if the answer to the question is what is required, then it proceeds to the next question. So each intermediate or split point evaluates one or more predicates. So we split the data based on whether it satisfies a predicate, that is whether the answer is right or wrong, is true or false, and then leaf level nodes will be associated with classes based on the majority labels. That is, depending on how deep we go, sometimes we might not want to go deep. A decision tree will just have, let's say, 2 stages or 3 stages, but some they might be deep. So they might have, let's say, 10 stages. So depending on how deep we go, there may be multiple levels on the data. So easy to use in scikit-learn. Scikit-learn is easy to use, although we will want to know more about how they work. All right. So how a decision tree is built, from the basics to an algorithm, we now understand how a decision tree works and represent an explanation of the decision points in making a classification. We saw an informal means of deciding how to choose the intermediate node, and then let's see how we can formalize this into algorithm. And the basic approach is at each point find a future and condition to split the decision tree. do this at the root. So we will have a root and then divide the training set into subset depending on the condition and then repeat recursively on each of the data subsets. The question that should come to our mind are, does it matter which condition and feature we use? And the answer is yes. So you need to know, as I said, you need to use the right features. Is there an optimal strategy? Yes, but it is sometimes hard. Okay, recent work does mixed integer optimization. The link is here. If you have access to this slide, just go to this link and you will find information on this. It's a paper, right? Wonderful. So this is a paper, I think, and it may need some optimal classification trees. All right, let's just go back to what we have. Here we go. So the greedy heuristic to build decision tree, that is one of the approach is what we call greedy heuristic. What you need to do is split data sets. If items, you begin to ask the condition, if item in the data set are not all of the same class, then determine a predicate over a feature that minimizes some notions of information to be defined later, and then partition the dataset according to the predicate, split each subset. So this may overfit to the training data. And another heuristic is generalize the tree by pruning off some of the lower levels, e.g. anything below a maximum depth. You know what pruning is? If you have a tree, you want to prune it, so you cut some of the branches, some of the leaves, right? So the same thing applies here. So sometimes if we have a very deep tree, it might lead to overfitting. It might not generalize well. So what we do is normally we just prune it. We cut some of the lower levels, and we might have a threshold before doing that. And then, so how to define information gain and compare the data set, pre-split versus the combination of split data sets, measure purity, whether all data is in the same class. And then the first idea is use entropy from information theory as the basis of comparison. Entropy is just a matrix that you use to compare and see how well the comparison works. All right. And then so entropy, we go deeper into it. It has some mathematical notations here, but don't worry about this. Entropy is a entity that measures the number of bits of information required to capture a signal, or required to take a decision, in other words. So example, values in a stream of samples. So suppose y is a random variable with possible values. Let's say you have y1, y2 to yn, and each yi occurs with probability py. Then the entropy is defined by this equation. Hy, that is entropy of y, equals to the summation of I equals to 1 to n, and then the probability of I, and then logarithm. We are dealing with binary numbers now, so logarithm to the base 2 multiplied by the probability of I. So I can take any value, please. It can be 1, 2, 3 to n. N is the total number of samples that you may have. And if you plot, if you say you represent this with some values for n, and then you plot, you can see that it starts like this, goes up, and then the maximum is 1, and then come down. So what is this telling us? That it can either, the maximum is 1, the minimum is 0. So it can either be 0 or 1. It's all about probability. Probability can either be 0 or 1. So, and that is what we want when we do classifications. Classification models are developed from the idea of our statistics. You remember we say data analytics, the main idea comes from computer science, statistics, and mathematics, and then they can be applied to any field. So what we are doing is we are just doing doing a probability whether it's gonna be 1 or 0, but we must have a threshold. Okay, so entropy for 1 bit, and then an example of entropy is here. We have an input data. So major, like, starts. These are some sample, all right, from 0 to 7. So we have 8 samples here. So entropy of input data, this is a function. It has been already written. So whenever you see def in Python is a keyword that we use to define or to develop or create a function. So the function name is probability, and it has an argument which is called a variable called term. And then the function is written. At the end of the day, it will return what? The entropy. So for instance, if we want to implement what we have seen previously using code, this is something that you might likely write, okay? And then so look at it here. We have, if this code is run, so it has some values here, math 0.5, and then start, and then what we're more concerned about, the entropy of like start, which is equals to 1 now. And then you can plot it and see. So conditional entropy, how do we formalize the difference in entropy after we split? Let's define conditional entropy. This is a conditional, this is from statistic, please. This, when this is true, okay? This holds when this is true. And then define specific conditional entropy. So if x is equals to, this is true for x is equals to v, to capture entropy of y hat, that is predicted value of y for the subset of the data y hat meeting the condition x is equals to v. So this condition must be fulfilled before this value will be obtained. So then we can compute a weighted average entropy, assuming that x is equals to vi with the probability py. The equation is here. So just don't want to be bombarding you with these technicalities. An example of conditional entropy, the same thing that we saw before. Just want to see if we can have some codes here. So from conditional entropy to information gain, the same thing is conditional entropy to information gained. And then what we are doing is we split using the predicate that maximizes information gain. So these are, when you hear information gain, from information gain, we'll proceed to gain index, a Gini index. All is a matrix that what we are using to evaluate the performance of the classifier. Nothing more about this. So entropy isn't the only possible metric for information gain, right? So we have Gini index. That's what I was saying before. So instead of entropy, we use Gini index to measure how often a randomly chosen element from the set will be incorrectly labeled. Not sure how many slides we have remaining. So the summary is decision trees and split points. Choosing a split point or predicate for intermediate node is heuristics based. All right, and then we usually look for a split that maximizes information gain, that is, minimizes the error, the prediction error. And another measure is called the Gini index, which is what you will be using when you start implementing decision trees on either Google Colab or any of the platform that you'll be using. So finally, note that unlike many supervised machine learning algorithms, decision trees are scale invariant. So normalizing or scaling the data doesn't matter. So you can work with decision tree because it's one of the interpretable machine learning. Sometimes you don't need to normalize or scale the data. You can just try it and see what works. So decision trees and overfitting. Major danger of decision trees is what we call overfitting. To summarize, as I said, overfitting is when the model performs well on training data, and then has a poor performance on the testing data. We say the model is what? Is overfitting. Some of the ways we overcome this is by applying some non-supervised machine learning like the PCA, principal component analysis, to what? To remove or to get to extract the features in the data set and then use the important features to develop the machine learning or to decision tree classifier so that it can generalize well at the end. Another approach to make a classifier more accurate is what we call ensembles. So in terms of ensembles, you train classify over different subset of inputs. So you will have not only one classifier, but you will train many classifiers. For instance, classifier 1, classifier 2, classifier 3, classifier 3. That is where the name ensembles come from. And then at the end, you take the average of these classifiers, the average of their predictions, and then that performs the final classifier. So by combining, so classifier combines votes of ensemble members. So you have one classifier at the end. So it's one of the approaches of improving the accuracy and then overcoming the challenge of overfitting. So ensembles of decision trees, one of the ensembles of decision tree is what we call random forest. Is a very good model, and also you can use the scikit-learn to just call it and then make use of it. So random forest, this is how it works. You draw a random bootstrap data sample of size n with replacement. This is what we call bagging, and then you build a tiny decision tree, and at each node randomly select the candidate features and then split the nodes using the feature with best split according to objective function, that is the information gain now, and then repeat to produce k decision trees, that is where the name forest come from. And then for prediction, use majority vote to for a new data. This is just a few steps or explanation of what random forest is or how random forest works. So random forest hyperparameters, as I said, hyperparameters, every machine learning model has hyperparameters in, and it's your duty to find the suitable values for these hyperparameters that will generate the best trained model. So how many trees is one of the parameters. Number of trees, we call them estimators. The depth of the tree is another parameter. The size of the candidate feature is another parameter, all right? So you need to assign some values. So if say you want your tree to have, let's say 3 stages, you will now assign a value to the depth equals to 3, how many estimators, and then how many classifiers do you want to train? Estimators equals to 10, that is you want to train 10 classifiers. So random forest in scikit-learn. So look at it, example here from sklearn.ensemble import random forest classifier. So you are calling this package to perform the classification task for you, and then you assign it to this variable CLF, and then these are the parameters that we see, hyperparameters. So n estimators, number of classifiers equals to 20. That is number of estimators, and then maximum depth, the maximum depth of the tree for each classifier equals to 2. It's okay, we are dealing with 2 hyperparameters here, but maybe you might need more hyperparameters when you want to perform some challenges. I can attempt. I see there are some questions. Just give me a few seconds. So now after defining the classifier, assigning some parameter values to the hyperparameters, then you train it using the fit, clf.fit, then you impute the training and then the y. So you are using the training data set now, the training input and then the training output variables. And then after that, then you make prediction. Predict equals to clf.predict. Then you use the testing data set. You must have splitted this data set before. And then you want to see, you are using accuracy as a performance metrics. You want to see the accuracy of the prediction now. So when you run these calls, you see that the accuracy is 98.1, which is very good accuracy, right? Let me see, like, can you explain the metrics again? 100. It's a cut. It's a bit unclear. Okay, so maybe I will go back. Where's the slide? 1, 2, 3. Okay, here, right? This matrix you mean, who is this? Roslyn? Is it here, right? 1 and zeros. So look at it here. We are dealing with signals here. It's not a real numbers. In computing, logic gate, some of you do, if you have idea of physics and then binary computation, if signal is 1, we are dealing with, let's say, Boolean values, either 1 or 0, or true or false, yes or no. This is what we are doing here. We are not dealing with some samples here, okay? All right. So what we are just saying here is, if we are using this particular feature, look at this. Let me just concentrate here. We have a table here, and this table has what? Let's say has 4 features: black, fury, small, and active. Okay? So if, for instance, we are using only this black as a feature to predict whether Y, the output, is a cat or is not a cat. Okay? And as I said, if the value for the Y in binary classification, if the output is 1, which means the answer is yes or is true. And if the value for the output, which means it means that the answer is no or is not true, the prediction is not right. So look at it. If we are just considering, we want to classify this cat, and then we want the future of this cat, which is black, we want black to be true. If black is not true, then let the output be 0. Tell us that this is not a cat. So look at it here. And remember, we say 1 is true, 0 is false. Okay? So for this, under this future black, we have a value 1, which means 1 is true here. So if the future for black is 1, then predict that this is a cat. And then how do we understand? The prediction value is 1. The same thing for the second row. We have future for black is 1, even though future for fury is 1, but we are more interested in the value for the black future. Already is 1. And the same thing is telling us that the output is Y, which means the component, or the what we are trying to predict is cat. But if say, for instance, we have 0 here, look at it here for the second table. So we have 0, 1, and then 1. Okay, so for the black is 0, even though fury is 1, and then this is 0, 0. Look at, I'm more concerned about this one. So second output is what? Is 0. Okay, so it's a bit abstract. This is binary. So what we are saying is, look at the future. Is the value of the future true? If it is yes, then tell us that this is cat, and then we know this is cat by the value of the output, which is 1. But if the value of the output is 0, it's saying that it's not a cat. I'm not sure if you get something from this explanation. True negative and true positive. Is that? I think it is the next slide, the square. All right, so we don't have much time, I think. Maybe later on, we will talk about this, please, and during break or any other time. So where did we stop before? Major dangers, yeah, overfitting, and then ensemble, which is random forest, and then bagging. So hyperparameters, you need to know what hyperparameters are. Summary of decision tree and random forest. So decision trees they are fast scale invariants, and then can handle categorical and continuous data, and then understandable. They are prone to overfitting. That is one of the drawbacks. While random forests use a form of ensembles called bagging, highly accurate, and then don't require. So random forests are one of the most popular and accurate methods that we use to perform classification. I'm just trying to see, yeah, to see if we can have a look at the Python code, which is very important. May I know if you have access to all the folders, the items in the folders, day 1, day 2, day 3? Previous videos of this session. Yesterday, I think you have been given link to watch. And then don't worry, or previous sections, I think you've been provided link yesterday to watch the recording. Am I right? No, where do I get the files? All right, so you don't have access to this file. Wow. Just if I need to do some things now. But so how are you going to do the hackathon then tomorrow? Sorry, let me just stop sharing now and then I will share again. I need to go to my Google Colab and then see what we can get from there. Right. Time is fast spent. No. New. Okay, let me share my screen again. Can you see my screen, please? Right, so I just want to open a Google Colab. All right, so let's go back. So you can see my screen. This is a untitled Google Colab. And then I hope you have been taught how to upload a notebook to a Google Colab yesterday. I think I have the 3. Okay, so this is what I was explaining before, looking at it practically, hands-on code, okay? So let me just run this and see. So I'm in Google Colab now, and this is polynomials. I don't want to go into polynomials now. Let's just go into polynomials. Let's try and classifiers. You can do classification with polynomials. So we have tried logistic regression. What about decision tree? So I'm just trying to see. Let's look at decision tree. So you see from ELAN, your tree import decision tree classifier. So let me run this cell first and see if it works. Then fine. Then we go. All right. Model trend fit. There are some data that I think we need to work with them. So I need to run the previous cells. So just let's run the previous cells and see. This is just polynomials, but we don't need this. And then what about polynomials? Polynomials. Let's try some extract. Okay. Do you have access to this notebook, Jupyter notebook? What is the answer? You have access to it, right, Emmanuel? Okay, thank you. So you can run it on Google Colab, please. How will I get that? I think you need to ask Mariam. If you watch in the morning, I was also struggling with some of the materials in the folder. So please, any query, just forward them to Mariam. She's the lead, module lead, the course lead. All right, please. Thanks. All right, so let's run this. I'm not interested in this. So this is a plot. These are all how to implement polynomials in using Python. And then you have some plots. So if you have the notebook, you can run them and then you can see all these results. I'm just interested in how to implement decision trees on Google Colab. We run the code and then see how it works. All right, so let's move forward. These are all classification using polynomials. And then here we come. All right, you see I have an arrow here because it says there is a file that has a data. Look at it. It says whenever you run into arrow, you will run into this type of arrows. Look at it. It says file not found arrow, and then it says no such file or directory that is called saheart.csv. So I am trying to use a data that is now in an Excel form, in a CSV form, and then it's called saheart, but I have not uploaded it here. That is the problem that we have. So the error is from this line. So I'm trying to read a file, a data file, which is not uploaded. So yesterday, I'm not sure if you have been taught how to upload. If you have a data, you can upload the data onto your Google Colab, and then you can now make use of it. So this is how I will do it. I will click at this arrow, upload, then I will find where my data is. Remember, this is the data, saheart, that we will be using. And then I will say open, and then I will say okay. So this data is uploaded now. It's in the virtual environment of Colab, and then I will close this, and then I will run this cell again. So no more arrow. So the data is now available. All right, so I'll go down. So this is the data set. You see, these are the last 5 rows of the data set. These are the attributes. Name, SB, I can go. So these are the attributes that we have, the features. So remember, we say they are in rows and columns. Rows represent data sample. Columns represent the features, the input features. And then this is the classes. We want to define either farm his is true or false. So the class is either true or false, 0 or 1, yes or no. So we only have 2 outputs and for the y variable. That is why we call it a binary classification. Okay, so and then this is I think using polynomial, using a training, and then we're just trying to use polynomial to classify, but you can run through this cell and then see. Just want to see, this is logistic regression. You treated it yesterday with Khalid. So you can use logistic regression for classification as well. So look at it. These are the accuracy, train accuracy, test accuracy. I'm just trying to jump to where we will use decision tree. Okay, this is for logistic regression nouns. The training accuracy is 0.72, and then the test accuracy is 0.75. So now, so we have tried logistic regression previous. So what about decision tree? This is where we're going to pick it up. So we call a decision tree classifier, and then going so fast. All right, so we run this cell. This is the classifier, decision tree classifier, random set is 0. So we now call the fit. You remember dot fit, the train, and then the Y train data set. This data is split into train and Y train data set. I believe is done here previously. You can see it from here. This is where the data set have been splitted. X train, Y train, X test, and then Y test. And this is what we'll be using subsequently, okay? So they have been splitted already. So, and then next is now you print them, and then what do we find here is now training the decision tree using the fit, and then after fit, then we have some plots, and then we calculate the training accuracy and then the test accuracy. So the training accuracy is 1, and then the test accuracy is 0. What is this telling you? What problem do we have here? When the training accuracy is high and then the testing accuracy is low, what is it called? The model is what? Any answer in the chat? Right, let's move forward. So the model is overfitting. This is an overfitting. Yes, overfitting. Nice. So the model is overfitting. All right. So when we move forward, this is another plot for future importance. Now it's telling you which future contributes to the model output. It's a very important future importance is one of the things that we benefit from decision tree. So then we can also plot the tree, decision tree. You can see it here. This is the decision tree. You can see the depth and all the Gini index values. And then this is telling you how the decision tree arrive at what? At making this classification, right? And then combining the trees forms a random forest. These are the prone to overtraining through. So we want to now get rid of this overfitting problem. So we want to try random forest now. We say random forest is example of is one of the ensamples models that trains so many classifiers and then combine them and then take the votes from there. So look at it. We imported random forest classifier and then we give some parameter value, number of estimators 10, and then random state is 2. That is what the depth, right? So after training, accuracy is now 0.97, and then train accuracy is 0.97, test accuracy is 0.71. Yeah, even though there is an improvement in the test accuracy, but still overfitting. Okay, so what about this? When we click this, we have the future importance for the random forest. And then there is what we call K nearest neighbor is another classifier that you can use. So we can import it. It's imported here. And then when we run this, it gives us all the training accuracy for the value of n, that is when n is 3 and 4 and so on and so forth, is another classifier that you might come across. And we have not treated it, but for your own sake, you might try it. I'm not sure if you have come across support vector classifiers from support vector machine. This is the code for it. If you run it to classify this, we can see the accuracy for the support vector machine is there is a parameter that we call canal. If the canal is C is 50 and then gamma is 0.1, this is the train accuracy 1, testing accuracy is 0. The model is still overfitting. So I think this is the problem that you may encounter when you come for your to do your hackathon, and your task is to see how to reduce this to improve the performance of the model. That is, make sure that the model does not overfit. And a model that does not overfit is we don't want to see a huge difference between the testing accuracy and then the training accuracy. And we want the model to attain a reasonable accuracy value, right? So which model performs best? If I run this code, it says model tree errors, random forest, and then logistic regression. So this is a comparison, but we are using the testing error. So in this case, which model performed best? Best model is logistic regression. Why? Because why logistic regression? 0.75. I think, yeah, I think like it has the highest accuracy, right? But what about, it's not, it might not only be the only parameter to to determine the performance of a model. This is a homework for you if you have access to this notebook. So handwritten digit analysis. So from sklearn, you will import this hand digit data sets, and then you need to prepare the data sets. Let me see. You prepare the data set here, and then there are some tasks for you here. Put your code here for the digit data set. Try different models, build an ensemble, and then see what happens if you change which data is in the training and test set. And then also, what if you change the proportion of the training test from 70? So the data set is given to you, is already splitted into training and then testing. You need to just call these models, supply them with the training and testing data set. It's also a classification task, and then run it and see what will be the output of each model. And then by fit, does that mean the training data is too specific? I am not sure. It's not that the training data is too specific. There are many things that will lead to overfitting. Sometimes if there are noise in the data set, all right, or sometimes if there are some discrepancies in the data set, if the data set is not cleaned well or is not filtered well, it might need to overfitting. Sometimes also depending on how the data set is being splitted. If sometimes we split training 80% and then testing 20%. If it's still overfitting, you can try splitting it into 70 and 30%. And also, these are some of the reasons why model can overfit. All right, so I think we need to stop here. Sorry for the technical issues we encounter at the beginning. And then I hope you may find one or two things helpful in the course of this. I am not sure if Mariam has sorted out the issue of the data explanatory, which we will do it in the next section. But may I request that we come back? This is 11:37 now, and then we are stopping at 1 o'clock. So can we come back at 11:50, 10 minutes to 1 for the second section, please? Is that okay? All right, then I'll see you